Okay, so we have another example here, and we want to state the domain and range of this function right here. And if you'll recall, the way that we stated finding the domain and range of a function before is if we knew the location of the vertex of this parabola. And I like the completing the square method for finding that vertex of the parabola. But I'll note that a lot of people, well, they look at that, they go, Mr. Peoples, come on. Really? Isn't there a better way? It, well, there is no shortcut, right? But just so that you know, there is a formula, but I can't do it without developing the formula. So you'll have to stick with me if you want me to develop the formula for you. So here it is. If I had y is equal to something of the form ax squared plus bx plus c, and I was interested in completing the square in this guy in order to do this, I will tell you that what's going to happen right here is that I would have to take my first pair of terms right here and isolate them and factor out a. Well, what does that mean for me? A would be x squared plus, it would have to be b over ax plus c. And I would have to complete the square inside of this parenthesis right here. And if I did that, y would equal a times x squared plus b over a times x. And then we'd have to add half of this coefficient, b over a squared. Well, what is half of b over a? 1/2 of b over a is b over 2a. And we would have to square that to complete our square. So b over 2a squared, right? And we would have to subtract that away at the same time. And I'm not going to go through the entire development right here because I know you just hated everything I just did with those fractions right there. But take a deep breath, it's actually okay. The main point that I wanted to get to you right here is the following. If we were to rewrite this one more time so that we had our perfect square trinomial in the parentheses, would look like this, plus b squared over 4a squared, I guess, minus a times b squared over 4a squared plus c. And some of this might actually look kind of familiar to you, especially if you remember the development of the quadratic formula. Y would equal a times x plus b over 2a quantity squared plus something. I'm not that worried about the something over here, but I am worried about this guy right here, because this is actually the location of my vertex's x-coordinate. Of my vertex, I would find it at x equals, whatever makes that 0, and that would be negative of b over 2a. So, if you keep that in mind, we identify a here as 1 in this function g of x. We identify b here as negative 1, and we identify c as negative 2. So how do we use that? Well, the vertex will have an x-coordinate at the point negative b, so the negative of negative 1 divided by 2 times a. That is at x equals positive 1/2. Well, that's all well and good. What about the y-coordinate? Well, the y-coordinate is going to be found by substituting in this value, x equals 1/2, into our function. So in fact, we have to find the value of g of 1/2. In this case, that would be 1/2 squared minus 1/2 minus 2, which is to say 1/4 minus 1/2 minus 2 1/4 minus 1/2 is negative 1/4. We're subtracting from that 2 over 1, which is to say negative 1/4, minus 8/4, which is to say negative 9/4. So our vertex is the coordinate point at 1/2, negative 9/4. Now once you find that vertex, what do we do with it? Well, it implies, because this function is a polynomial, the domain is all real numbers, but the range is limited by the location of the vertex. And in this case, the range depends on where the y-coordinate of the vertex is and whether the parabola opens up or down. We know this parabola opens upward. That's because our leading coefficient, a, is 1, and it's going to start at the y-coordinate negative 9/4 and continue on to positive infinity. So that would be our answer. Okay, more stuff in the next video.